Well, let's do a quick summary of Biot Savart. So Biot Savart law. You use this to find magnetic field due to moving charges, and if you have charge Q, and charge Q moves at some speed or velocity v, and you're interested in a magnitude, or you're interested in magnetic field at some point here, distance r away, then you can find that by doing the following. The magnetic field E is mu naught over 4 pi times Q times V cross R hat over R squared. Alright, so that would be in a vector form, and of course this amounts to, with the magnitude, you would do sine of this, so 4 pi times Q times V times the sine of the angle theta times, well, 1, magnitude of R hat, divided by R squared. That's one thing you can do with it. Second thing that you can do with it is you can take this expression and you could turn it into an infinitesimal expression, and this is usually how this law is stated. So this is mu naught over 4 pi times dq, and then you would have v cross cross r hat over r squared. You have that, and then from here you can turn it into an expression for the magnetic field due to a current. So this would be mu naught over 4 pi times I, and then you'd have dl, a segment of a wire dl, crossed with r hat over r squared. And now what this picture means is that if you have a wire runs like this, and you have some current that flows through this thing, then you would consider some small section dl here. Now let's throw a different color on this. You would consider a small section dl, and then from this small section dl, some distance r away, you could calculate magnetic field dB at this specific point. And so that r, this r here, that's this r and this r, dl, that's this dl, and then I is just the current that flows through this wire. So this is some sort of a conductive wire. And using this equation here, we found magnetic fields for a straight wire. A straight wire, I, some distance, perpendicular distance d away. You have an expression for the magnetic field. You need to know what that is. Let's see if I can look that up. The expression for the magnetic field is this: some distance d away from the wire, and then L is the length of the wire, whatever that length might be. So if it starts here and then it runs to this point, then this would be the length of the wire L. Now, if this distance d is very, 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 very small, then this magnetic field simplifies to mu naught I over 2 pi times d. But this is if d is a lot smaller than L. Okay, so we had that. We also derived the expression for the magnetic field due to a loop. So let's state that, and I think that will do for this brief summary. So if you have a loop, I guess that'll do. So the current flows into this loop, flows through the loop, and then comes back out of the loop. We have an expression for magnetic field along this axis at some point. I think we used x. That was x away. Magnetic field at this point is, well, let's give this r. So magnetic field here equals this. And just so big R is the radius of the loop, and X is the distance away from the loop itself. And if X is 0, so if X is 0, then you get the magnetic field right at the center of the loop, which is simply mu naught times I. Let's see what that does. Over 2R. Yeah. Alright, so you get that, and this is going to be very useful later on. So will this be useful later on? We just draw a picture here. So if you have a loop and there's a wire that flows through this thing, you use the right-hand rule to determine the magnetic field direction. But at the center, the magnetic field would have an expression of mu naught times I over 2R. Alright, well, that's a brief summary of Biot Savart law and what you can derive with it. You should know how to derive these things. I think at some point if I have a quiz on Biot Savart, I will probably ask you to do one of the derivations. You should also know how to solve, well, essentially all of the problems that are in the worksheet. Okay.